We are happy to have Professor Nikita Nekrasov from Stony Brook. He will be talking about BPS CFT correspondence. Yeah, this is the first of the two technical talks in NARC lecture series. Yeah.
Thank you.
So there will be one more talk in Friday.
Thank you very much for coming back after yesterday's renormalization lecture. So today's talk will be indeed a little bit more technical, but probably not too technical. Well, but if you have any questions, please ask. There is a blackboard. I can maybe give more details, or we can make a different talk altogether. So this is a report. It's in a way it's a report on something I've been working on more or less all my scientific life. So it's I'm sorry to say it's been a long time now. So I've collaborated with lots of people on that, and including my students and postdocs, and one of my former students, Navin Prabhakar, so he made the great contribution to this topic. So what is this topic? So this topic, of course, the name is a little bit of a joke, but it's a serious name. So it's a correspondence which I introduced 20 years ago, more than 20 years ago, which came from the observation that certain exactly computable correlation functions in supersymmetric gauge theories are not only computable, but what they're equal to happen to be correlation functions, or more precisely blocks, conformal blocks of two-dimensional field theories, conformal field theories, or the integrable analogs. And so this correspondence at first was very surprising, because on the one hand you have four-dimensional physics with things which can be propagating in four space-time dimensions, and yet you can find a set of special observables whose expectation values are not only exactly computable, they're actually sensitive to non-perturbative physics, and yet they're exactly equal to something which corresponds to the two-dimensional theory. So there is some kind of a Maya story from yesterday, where you have degrees of freedom which are defined in one number of space-time dimensions, but the same correlation functions can be reproduced by degrees of freedom which are defined in a different number of space-time dimensions. So if you only have access to this limited set of observables, you really don't know where you are. And so there is a lesson about this from this. Yes. So the connection is that, of course, there are many common letters. Okay. And there is a correspondence. But more seriously, one way we understand this correspondence is that so the basis for CFT correspondence is string theory. So which says that there are certain extended objects in non-perturbative string theory which can be described in different ways. And one description, at least at lower energies, is that of four-dimensional gauge theory. And another description, also at lower energies, but the notion of energy is different, is that of a 10-dimensional superstring theory on special background. So here, but there is an ambient 10-dimensional full string theory, which kind of encompasses both descriptions. So here is a similar story, except that from the 10-dimensional string theory, you can actually decouple a 6-dimensional conformal theory, superconformal theory, and the 6-dimensional theory then can be looked at in two different ways. And in one way, you see something which looks macroscopically four-dimensional, and another way, it looks something is macroscopically two-dimensional. So 6 is 2 plus 4. So this encompassing 6-dimensional theory is a kind of a Fourier transform which you can use to go between 2 and 4 dimensions. So that's one way, and that's in that sense they're similar. The difference is that ADS-CFT correspondence is conjectured to be very powerful, so to be the exact equivalence of full theories. So far, it has not been checked or proven, but there were many checks. Most of these checks were concerning the special observables, the same kind of observables I'm talking about, with some exception of, which maybe I'll mention, but it is claimed to be very powerful. We don't have access to this to the full power yet, but people make predictions using this, assuming this conjecture. This correspondence is a bit more restricted because it claims the exact equivalence only for a restricted set of observables, but on the other hand, it is on a much better mathematical footing. So many aspects of this correspondence are proven. So in that sense, so that's the what's the same, what's different. Now, this correspondence, well, let me explain more about this. We will see. So a little bit of history, what led to these ideas and what led to the main claims. In so 30 years ago, right, 31 years ago, Waff and Witten studied the maximal super-Yang-Mills theory, the same theory which is on the one side of ADS-CFT correspondence. It's the CFT of ADS-CFT. But they studied so-called twisted version of that theory, where the fermions and the scalars actually have different spins from the conventional assignment of spins to theory and flat spacetime. So they were studying this theory on various four manifolds. So the reason you need to do this twist is to preserve supersymmetry. So if you take the conventional super-Yang-Mills theory and make space-time curved, you will break all supersymmetry and basically you don't know anything about that theory. But if you make some reassignment of spins to fermions and scalars, then there is something which can be said about this theory. And they did this because there was a conjecture, earlier conjecture by Olive and Mantonin, which said that this maximal super-Yang-Mills theory actually enjoys the exact electric magnetic duality. So in maximal theory, you have two equivalent ways of formulating the maximal equations in empty space. So you can use electric fields or magnetic fields, and there is a way to map one to another. But maximal theory is free, so it's not really a very meaningful statement unless you are on the curved spacetime. But the conjecture was that if you do this for non-abelian theory with maximal supersymmetry, you still have the analogous duality. And this duality in particular inverts the gauge coupling. And more precisely, if you have a gauge coupling and theta angle, you can combine them in this complex parameter tau, and this parameter gets basically inverted. So what Waff and Witten showed, conjecture, this was a physics paper, observed, was that on one hand, they argued that the partition function of n equals 4 super-Yang-Mills computes is a generating function of the Euler characteristics of the modular spaces of instantons on this four manifold, which you studied in theory. And it is actually, so if you multiply it by some prefactor, which depends on the Euler characteristics of the manifold itself, this generating function becomes modular. So it transforms into itself, or it transforms in some simple way under the transformation which maps tau to -1 over tau. Yes?
Instantons on X.
Instantons on X, yes, on this manifold. This is the gauge group. Yes. So there are some refinements that actually the groups, so if depending on the group which you see on the dual side is not always the same group. it's now called Langland's dual group, and so there was this whole connection to Langland's program, which was a source of much excitement. But let me not stop there. Well, I have to stop. I just said it. But the thing is that this duality can be actually embedded into a larger group, which is the subgroup of the group of 2x2 matrices with integer coefficients, which act on this parameter tau by fractional linear transformations with integer coefficients. And so if you're a mathematician and you see such transformations, then you immediately understand that this parameter tau is actually a modular parameter of an elliptic curve. So for this picture, so the complex number tau with positive imaginary part defines an algebraic curve called elliptic curve, which you can describe in many ways. But the main thing is that if you change tau to the fractional linear transform A, B, C, and D, an integral 2x2 matrix with unit determinant, you get the same. You get isomorphic elliptic curve. So what this transformation does, it just changes the basis in the space of one cycle. So what you call the first cycle, what you call the second cycle, just changes the basis in this lattice, on this lattice. So this lattice generated by 1 and tau. Now another element of the story was the discovery of Hirako Nakajima, who at the time was the beginning Japanese geometer. Nowadays he's the president of International Mathematical Union. So he found that the modular spaces of instantons on special spaces, so these are so-called ALE manifolds, studied by Gibbons and Hawking and Iguchi and Hansen and others. So these are interesting four-dimensional solutions of Einstein equations with Euclidean metric. So these are Euclidean, sometimes they're called Euclidean gravitational instantons. So if you study gauge instantons on top of these gravitational instantons and look at the modular space of those instantons, then and then you study the cohomology of those modular spaces, which in physics terms would be the ground states of supersymmetric quantum mechanics. Then what Nakajima discovered was that this space of the union of these cohomology groups is actually a representation of Kac-Moody algebra. And this Kac-Moody algebra is related not to the gauge group. The only thing which gauge group determines is the level of the representation, but to the topology of this gravitational instanton. And so he used the duality, which is called Mackay duality, between them. So between the subgroups of finite subgroups of SU2 and simple Lie groups, so-called ADE classification. So here is the example. So so these subgroups of SU2, they come in three types. So there are two infinite series and three exceptional examples. And the same is true about the Lie groups, simple Lie groups. There are two infinite series, A and D type, and then there are three exceptions. So the A type corresponds to the cyclic group, which is just the group of rotations in 3 dimensions around one axis by the angles 2 pi over n. So you can embed it into SU2 as the group of diagonal matrices with these eigenvalues. And the dual group, Mackay dual group to this finite group is SUN. So Zn is dual to SUN. If you add to these cyclic rotations the reflections, so that the dual group will be the group SO2n, so that's a D series. And then there are the symmetries of Platonic polyhedra. So tetrahedron, octahedron, and icosahedron, and they are dual to the Lie groups E6, 7, E8.
I have a question. What is the rule of this duality?
The role of this duality.
Rule. How should I find the duality?
Yeah. So one way to so let's see. Maybe I'll talk about this. Oops. Okay, I didn't talk about. Okay, so one way to understand this duality. I mean, so the way Mackay constructed it was the following. So if you have a group gamma, so it's finite group. So you look at this set of its irreducible representations. Set of, and you just picture them as points. Okay, so each vertex. So I'm going to build a graph. So each vertex would be an element of this set of irreducible representations, and then you do the following operation. So because by definition it's a subgroup of SU2, the two-dimensional representation. So this is the representation spin 1/2 is also a representation of gamma. So I can take the representation which corresponds to any vertex and tensor multiplied by C2, and then decompose it the sum of irreducible representations with some multiplicities. And so if the representation J appears in this decomposition, well, you connect these two vertices with Aij edges. And so what Mackay showed is that just from the fact that gamma is a finite subgroup of SU2, so you build a finite graph with some structure, and so what he showed is that the graphs you get in this way are of only 3 types. So one type is it's the n-gon, n+1 gon. So this is what you will get for the group Zn. The group Zn being abelian, all its irreducible representations are one-dimensional, and in this, so they are labeled by the way the generator of this group acts in this representation. So it acts by multiplication by some nth root of unity, and there are nth root of unity. So there are n representations, sorry, n-gon, with including the trivial one. So there is one vertex which is kind of distinguished, which corresponds to trivial representation. So so for example, if you start with a trivial representation, so R0 is just one-dimensional space on which the group doesn't act, you multiply by C2. So this is the way the group Zn acts in C2, and so this is a representation of where omega acts by multiplication by omega, and this is a representation with omega acts by representation by omega inverse or omega to the power n-1. And so this is the graph. So this is how you start building this graph. So this is R1, and this is R-1. And then you have the same structure for other representations. So this is one type of graph you can get. Another type is of that type. So by the way, these vertices are all labeled. You can label them. You can attach to a vertex a number which is the dimension of the irreducible representation. And for Zn, all these numbers will be 1 because these are all one-dimensional representations. But here, this is something more interesting. So you get 4 ones and kind of a spine which consists of 2s. So this is A type, this is G type, and then there are. So remember that gamma acts on SU2, right? But you can see, so right. So these are like subtitles. So gamma being some group of SU2, it's a certain dimension when you add on C2, so you can take a quotient. The quotient will be a similar space, but the problem which you can resolve. There's a procedure which takes the singularity, blows it up, and replaces it by some kind of by a bunch of spheres. So there are small two-dimensional spheres whose intersections, by the way, are captured by the same Dinkin diagram. So this would be. So this would be for the G type, for example. So this you should recognize in this picture a truncated version of the graph which I drew before. So you can study type 2A string on such a background. So this resolution of singularities solves Einstein equations. So there is this. So there is. Again?
Can you extend that picture again with the hyperbola and the little discs?
These are not disks, these are spheres.
Okay, yeah. So what is going on in that picture?
I'm describing the topology of the space, of the resolved space.
So
and
the spheres.
Hyperboloid just means that asymptotically, the space looks like a quotient of Euclidean space by some group. So at infinity, you have so at infinity, you have not the three-dimensional sphere which you would have had for flat space, but the so-called length space. So it's a space where you have some identifications. It is non-compact. So so it's something which it's a 10-dimensional theory, but the small spheres, they sort of contain degrees of freedom which are attached to the spheres, and so these degrees of freedom can only propagate in 6 dimensions. And so what string theorists argued was that if you take the limit when the sizes of all the spheres go to 0, then you have the enhancement gauge symmetry. So there are vector multiplets which carry the symmetry, so gauge bosons plus superpartners. To the group which is Mackay dual to this group gamma. So in some sense, string theory gives you a construction of this group, of Lie group out of the finite group, but it's a so twisted sectors will give you the maximal torus. So the maximal torus of this group comes from the twisted sector fields, but to see the full enhancement of gauge symmetry, you also need non-perturbative states which come from D2 branes, which wrap these cycles. And so these cycles, they correspond to simple roots. And then so each D2 brane is like a W boson corresponding to simple root, or it can wrap linear combination of those cycles, so you have all roots coming. Yeah, they will be massless pools. They will be massless in the limit when the sizes are exactly zero. Okay, so So what I want to point out here is that this representation of Kac-Moody algebra, yes.
For these C2 mod gamma singularities and so on, the same resolution picture also extends for these for the exceptional.
Yes.
It does. Okay, I see. So
No, it's true for any gamma. So for any finite subgroup.
Oh, it's true for all of them. It's true for so all I see. And another question is, so the C2 mod, I mean, so the A series, you can also embed them in K3s and so on, at least for some classes, right?
Yeah. So for
but do the E series admit such compact embeddings?
So the question is, can you replace this space by compact space?
Yeah. So if you take K3, you can acquire singular points at which K3 acquires these local singularities of this kind.
K3, so you can take a limit when K3 surface will develop E8 singularity.
Yeah.
You cannot take a limit when it will develop an A100 singularity.
Right. It's some finite numbers.
Yeah,
exactly.
but all exceptional groups you can.
But the E series also, I see.
Okay, so but the point is that the point which I wanted to make here was a starting point was that these Kac-Moody algebras are the symmetries of two-dimensional conformal field theories, and so there was some kind of indication that something in the four-dimensional gauge theory hiding a symmetry which is specific to two-dimensional conformal field theory, but it's also hiding in a kind of intricate way that most likely in four-dimensional terms, the symmetry is non-local because one aspect of that was the instant-on charge corresponded to the energy in terms of the L0 for two-dimensional theory, and possibly mapping one quantum field theory to another. So it was kind of in the air. So it was early 90s. So there were some indications that there is some structure, but nobody knew how to approach it. And then an important tool which allowed to study these questions arose in the context of less supersymmetric theories, in the context of D equals 4, N equals 2 theories. And this tool is the Z function, or sometimes called Nekrasov partition function. It's a refined version of Wheaton index, actually, if you know what the Wheaton index is. So there's a formal definition of this partition function. It's a partition function of the theory where you took the adjoint Higgs field, which was a scalar in adjoint representation, complex scalar, and deformed it by adding to it a covariant derivative in the direction of a vector field which generates rotations of spacetime, Euclidean spacetime. There's some kind of weird deformation which uses rotational symmetry and therefore breaks translational symmetry. But it is possible to do, and it's less drastic than placing the theory on some curved four manifold. And therefore, maybe so it contains more information about the original theory. So this can be viewed also as a limit of a five-dimensional theory compactified on a circle of some circumference beta, where the four-dimensional space-time is twisted by the angles proportional to beta as you go around the circle. So it's some kind of twisted compactification. And so if you take the limit beta to 0, but keep epsilon 1, epsilon 2 finite, then the resulting four-dimensional theory will be slightly deformed. And that's the information which we want. So it turns out that one can compute this partition function exactly. This computation has a tree level, one loop, and non-perturbative parts. It breaks some supersymmetry. Yes, it breaks right, because the supersymmetry contains in itself the Poincare symmetry, and Poincare symmetry contains translations. And choosing the rotations breaks translations, so something has to go. But the trick is to preserve some supercharge, modified supercharge, which allows you to do computations. So one hint that there is interesting connection of four-dimensional theories to two-dimensional ones was that the one-loop computation in these theories was constantly spitting out this kind of double analog of the gamma function called Barnes gamma function, which was also showing up in Liouville conformal field theory, as was shown by Dorn, Otto, and Zamolodchikov, and was popularized by Fadeev after his works with Kashayev and Volkov. And this is, roughly speaking, the function which has a two-dimensional lattice of zeros or poles, depending how you regularize it, where B here is the parameter in Liouville theory, and it's related to this angles epsilon 1, epsilon 2 as through the ratio. But okay, but the most interesting part was that in this, after this deformation, you retained not only perturbative but also non-trivial, non-perturbative effects in gauge theory, and these were instant dots. And so this particular function could be computed exactly and completely for a class of gauge groups which are the products of unitary groups. So the example of gauge theory where the gauge group is a product of unitary groups is a standard model. So this is, one should be respectful of such choices. Of course, this is not the most general gauge group, but as I said, we use it in the standard model, so why not appreciate it? And so so there is a technique called localization, which I had to adapt for these theories, which allows you to perform these computations. And the result is connects us to the topic of yesterday's lecture. The result is that it's a summation instead of integration of over paths, over the field configurations. The result is a summation, so it's we gain some mileage, and the summation over the collections of partitions or Young diagrams. So for each factor in the gauge group, you will be summing over a collection of n tuples of Young diagram, where n would be the rank of the corresponding factor. So if I have k factors, then I will be summing over n1 Young diagrams for the first factor and 2 Young diagrams for the second factor, and so on. Now, the combinatorics of those n tuples of partitions can be mapped to be the combinatorics of Hilbert spaces of states of chiral bosons or fermions in 2 dimensions. So, for example, if you're if you study 2-dimensional CFT, one of the first examples of 2-dimensional CFT you learn about are chiral fermions, and you may study several species of chiral fermions. So, for special choice of this omega deformation, the special choice of angles when the one which corresponds to the SU2 rotation, this connection to free fermions becomes almost exact. And so let me just remind you something. So the partition or Young diagram is also you can also view it as describing a particular excitation in the theory of a single chiral fermion, where you take a certain number of states from Dirac C, and so you add a certain number of holes and electrons. And so the positions of holes and electrons will be encoded by the shifted row lengths of Young diagram. So the first you shift the first one by 1/2, the second one by 3/2, the third one by 5/2, and so on. At some point, your Young diagram is finished, so you just put lambdas, and so you have the infinite sequence of fermions whose labels now form an arithmetic sequence, and this is just a part of Dirac C. Now you can also replace, there is a procedure called bosonization. So sometimes you can express chiral fermions in terms of free bosons, and so the same partitions you will encounter in the studies of free bosons. And so But these bosons will be now interacting. So you know, maybe from the old work of Coleman, that sometimes you can map interacting bosonic theories like Sine-Gordon to free fermionic theories like a Turing model or massive Dirac fermion. And so this is where bosonization is useful. So here, the bosonic description turns out to be one of the very interesting two-dimensional conformal field theories, such as Liouville or Toda theories, and sometimes you get the deformations. So there are three classes of n equals 2 theories, which are, by the way, well defined, meaning they're conformal in the ultraviolet. And so these are three classes on which, for which these partition functions can be studied, and the connection to two-dimensional CFTs can be kind of explored and strengthened. So there are theories which have Lagrangians, so they have classical limits. There are theories which maybe not have Lagrangians, but whose using string dualities, we can understand them through the low energy behavior as defined by some auxiliary two-dimensional gauge theory, such as Hitchin system, on which I will be speaking more on Friday. And theories for which the partition function can be computed using string theory or topological string theory. So there is this kind of map of n equals 2 theories. Yes.
Sorry. So in the previous question section, so you mentioned two connections to 2D CFT. One was that the Barnes function kept turning up, and that has some connection to Liouville theory. But then in these particular UN cross UN cross UN theories, you connected to free fermions or free bosons.
So this was just an indication that the combinatorics, which of the partition function, is that of a bunch of free bosons and free fermions.
I see.
But I haven't yet gotten to the actual formulas, and so we
both of these are still indications.
Yes, just
okay. Sorry, thanks. Yeah.
So I just showed you the map of this space of theories, and there are some overlaps, but I mean these are kind of patches. So we are kind of exploring the space of quantum field theories. I mean there is a much bigger space of all quantum field theories in 4 dimensions, of which the supersymmetric theories form kind of a small piece, and inside this supersymmetric theories there are even smaller pieces which have names indicating the origin of those theories. So I'm going to say something about the theories which are so-called quiver theories. So the gauge groups are the products of unitary factors, and there are matter fields which are organized in a similar fashion. So in quiver, of course, there is a kind of Kurukshetra notion of a quiver, but this is a quiver in mathematical sense, which is the just oriented graph. But so graph has arrows, like edges are arrows, so that's why it's called a quiver. And so the way we so the vertices label factors in the gauge group. The edges indicate that there are matter fields which are charged under these factors. So if there is an edge connecting vertex I and J, it means that there is a matter field in the bifundamental representation. Now, in n equals 2 theories, the matter fields, they come in the form of so-called hypermultiplets. So the actually charged fields come in, so they are both bifundamental and its conjugate. So that's why you don't always specify the direction of the arrow. So the simplest types of theories for which the running coupling gauge coupling actually couplings. So they have many couplings for each. So for each factor, you have its coupling. Because you have matter fields, there might be non-trivial one-loop renormalization, and it turns out that there is a unique, not unique, but there is a finite number of ways of arranging the gauge factors and matter fields in such a way that in the ultraviolet, the couplings don't run. So you have conformal field theory. And it turns out that this classification of such arrangements is exactly the same as the Mackay classification of finite subgroups of SU2. So the equation, which I didn't write, but I will now write. So this equation is the vanishing of the one loop beta function for the gauge factor I. And this is the same equation which you got if you remember this decomposition. So if you just take the dimensions of the left-hand side and the right-hand side, you will get the same identity. So the numbers Ni, they have to be proportional to the kind of minimal solution of this equation when little ai is the so-called Dynkin label, which is the same thing as a dimension of the irreducible presentation of some group gamma. So here, it's a kind of reverse engineering problem. You start with a graph with some conditions on a graph with the assignment of numbers to the vertices, which solves this equation at every vertex. And it turns out that the only possibility for such graph is to be the graph which comes from some finite subgroup of SU2. And so this is the complete classification. So these are the promised graphs. So this was for E6, this is E7, and this is E8. And the numbers are maybe not very legible, but so it's 1, 2, 3, 4, and then it's 2. So 2 is 2 by 2 is 4, and 4 times 2 is 8, which is 3 plus 2 plus 3. So at every vertex, if you take twice the number which is written at the vertex, you will get the sum of the numbers which are at its neighbors. So this is kind of harmonic equation. Anyway, and so now if you have such a theory, you can now deform it by giving masses to some fields. And so out of these theories, you can produce many more theories which might be asymptotically free. And so you can end up with theories with the additional charged matter, which is in fundamental representation. So here is an example of E6 type theory with the gauge group, which is a product of these groups. And so to compensate for missing vertices, you have some fundamental hypermultiplets. So 1 is the number of these hypermultiplets. So the claim is that so if you can compute the partition function for the z function for such a theory, study its asymptotics when epsilon1, epsilon2 go to 0, and discover an emergent geometry of the type I spoke about yesterday, which will happen to be describable in terms of the auxiliary 4 or 3-dimensional gauge theory with the gauge group, which is Mackay dual to the graph. So it's not the graph, it's not the gauge group of the theory. It's something which is kind of emergent from the arrangement of gauge factors and matter fields. For example, in this, so it turns out that in particular, so to solve the U4 cross U5 cross U6 cross U8 cross U9 cross U12 gauge theory with this arrangement of bifundamentals and fundamentals, you need an auxiliary gauge theory with a gauge group E6. So what it means, what do I mean by this? What I mean is that the space of vacua, so this n equals 2, d equals 4 theory has continuous modular spaces of vacuum, of ground states, so states with zero energy, they are quasi-classically, they're characterized by vacuum expectation values of some scalar fields. So there are massless scalar fields. But quantum mechanically, the geometry of these spaces receives corrections. And so it turns out that these corrections are captured by the metric, which can be computed as this matrix of second derivatives of so this is imaginary part of the matrix of second derivatives of some function. And this function turns out to be a limit when epsilon 1, epsilon 2 goes to 0 of the renormalized free energy of the statistical model of these random partitions, which you see in the partition function. And so, well, so there is some special, so this is called special geometry. This is not an adjective, it's a technical term, special Kähler geometry. And it turns out that this kind of the neat way of describing this geometry is to say that this space is actually a base of some complex integrable system. So there is so you can upgrade this module space of Acua by adding certain vibration whose fibers are tori, like in the usual integrable system, so that the total space is the phase space. And so this phase space, it turns out that when you do some analysis, which took some time to do, so if you start with quiver gauge theory associated with one of these graphs, the total space would be the modular space of instantons on the space R2 cross T2 with the gauge group, which is this Mackay-Dull group. Yes, what is it?
So the tori, I assume, are like the action angle variables, like right?
Angle variables. Yes. So this will be angle variables. Angle.
The two angle variables at every point.
And these are action variables.
I see.
So,
and what does the modulus of the torus mean?
so this is a multidimensional. It's a multidimensional torus.
Okay.
And so it has not it's not just a modulus. It has the whole period matrix. This is the period matrix.
Right.
Which defines the metric on the base.
Yeah, but what does it mean from the phase space? Because phase spaces don't typically have metrics.
Right. This is the key word here. It's a complex integrable system. So in conventional real integrable systems, you have action and angle variables. But now imagine that your phase space is complex lexic manifold, your Hamiltonians are holomorphic functions, then these Liouville tori become complex tori. So they have twice as many cycles as the dimension.
I see.
So for example, if you think about the system with 2 degrees of freedom, so you have some Hamiltonian and so let's say two-dimensional with a two-dimensional phase space. So they're like harmonic oscillator, or maybe anharmonic oscillator. So the trajectories, let's say trajectories are some periodic orbits. So here, the action variables take values in something one-dimensional, right? So, and the angle variables are live on one-dimensional torus. But now imagine that this is complexified. So now this is C2. So this is now inside one complex dimensional space, and this S1 became an elliptic curve, like elliptic curve which I started this lecture with. But we're still in one degree of freedom. So now I can define two types of action variables by computing the integrals of the PDQ differential over A cycle, I can call it I sub A, or the B cycle, which I call all I sub B, they are not independent because they are both are functions of the energy level, but which one I use depends on my convenience. And moreover, if I go in this, so make some travels and come back, the choice of these variables may change. So there is some monodromy. So the fact that they are not independent means that, and so you can show that it means that there is a function, locally defined function, which I could denote by f, such that the B-type variables are actually derivatives of this function with respect to the A-type variables. So to appreciate this point, you need to go to the examples of more degrees of freedom, because then this will be vectors, but you still have just one function. And so the complex nature of this of the integral system produces the metric on the base. It's not the metric on the total space; it's the metric on the base.
I see.
Which you don't have in the real case. So it's something which is gained from.
Okay, thanks.
So this space is a globally R2 cross T2. I mean, the space on which so once again, the space on which the gauge theory lives is R4. I've solved the gauge theory in R4, and I'm re-expressing the answer in terms of some auxiliary geometry. So this R2 is not inside R4, and this T2 is not inside R4. It's somewhere else. It's a trivial bundle, yes. Okay, so now for special, in the A-type case, there are some dualities one can apply to the modular space of instantons on the space of translational symmetries, and map the instanton equations with gauge group SUK to the so-called Hitchens equations, which are kind of reduction of instanton equations to 2 dimensions on two-dimensional torus or a cylinder. So these are the type of equations you will get. And so this picture eventually leads to 2-dimensional CFT with a Kac-Moody symmetry or W algebra. And this theory will be of that type, with the singularities of this equation becoming the insertions of vertex operators. So my time is almost up, but I wanted to maybe briefly explain how one approaches. So how does one perform the sums of the partitions and proves proves the connection to conformal field theory or some generalization of it. And so this is and so there's some in this method there is some hope for something useful to be applied in more general quantum field theories. So the method is called non-perturbative Dyson-Schwinger equations. So let me just remind you something about the conventional Dyson-Schwinger equations, which is a set of identities you can prove, which follow from the fact that the integral doesn't change under small variations of the integration contour. So the usual Dyson-Schwinger equations are kind of quantum versions of equations of motion, that if you insert in the correlation functions the one more operator, which is the variation of the action, then so this n+1 point function can be reduced to the sum of n point functions. So you can reduce the number of insertion points where there will be a Planck constant, so it's a quantum correction, and so each of these operators will be changed by the corresponding variation with respect to the set of fields. So in general, this is a kind of it's not closed system of identities, so it connects n point functions to n+1 point functions, and so some recursion which doesn't help. But with some luck, if you make a clever choice of observables, maybe non-local, and maybe take some limit, then these equations become a closed system of equations which can be maybe analyzed. So, so one stupid limit, of course, is just a classical limit, in which case you just get the usual equations of motion. But there are less trivial limits, and one approach which is and so set of observables and one set of equations which some people still dream of making work are the loop equations. So your observables are Wilson loops, the expectation values of the holonomy of the gauge group of the gauge field around some loop gamma in the, let's say, fundamental representation of UN or SUN. And the limit is a 't Hooft planar limit. So it's a limit when the number of colors goes to infinity, the gauge coupling goes to zero, but the product of gauge coupling and n stays finite. So first, in this limit, the expectation values of Wilson loops factorize. And then Migdal and Makeenko in the early 80s wrote a set of equations which they claim are closed and so can be solved. So far, nobody managed to solve them, but still these are interesting equations. That there is some kind of a Laplacian acting on the space of loops, such that if you apply it to the expectation value of a single Wilson loop, you'll get a distribution on the space of loops which is supported on self-intersecting loops. And then, so the source of this equation will be the product of the expectations of the Wilson loops associated with the two halves. Now, so in the four-dimensional theory, nobody really succeeded in making these equations work, but in the zero-dimensional gauge theory, which is the matrix model, people use these equations quite successfully. So the analog of the loop equation, the loop observable, is this resolvent of the random matrix. So here phi is a random matrix, and one studies the action is just the trace of some polynomial of the matrix. And the loop equations become an algebraic equation on the expectation value of this shifted resolvent. Now, in interesting quantum field theories, the path integral is not just an integral. It also involves a summation over topological sectors, like instanton sectors. And so, for example, in gauge theory, we sum over the instanton charges. And so the dream is to supplement the set of Dyson-Schwinger equations corresponding to the small variations of the contour with a set of equations which correspond to large deformations of path integral contour, where locally in space-time you graft an instanton, small size instanton, which bumps you into a different instanton sector. So there is a connection between the space of gauge fields in the instanton with the instanton charge n and the space of gauge fields with instanton charge n plus 1. And so there might be some set of identities, some kind of recursive identities, which would involve the contributions of different instantons to the path integral. And so the compatibility between these two types of relations resembles the two ideas which people studied in the 80s. Again, one set of ideas is resurgence, and another set of ideas is the exact beta functions in super Yang-Mills theories. And so so time is up, right?
The gauge transformation that you talked about, should I think of it as a large gauge transformation or a field redefinition?
So this is really a change in field. So
yeah, field redefinition.
So it's a kind of a field redefinition which is dependent on the choice of a point in space and some local data. You know how exactly you modify the gauge field by adding to it. So this is small everywhere except some small neighborhood of a point X. And so there is a large gauge transformation which you need to perform around this point, but there is an additional change as well.
Okay, thanks.
So, okay, so to explain, give you a little bit more detail. So one finds an analog of the observable, like this loop observable, in gauge theory, which is kind of a quantum dressed spectral polynomial, characteristic polynomial of the adjoint Higgs field. So you define it as a, if you remember yesterday's talks, it's a kind of a pritistic exponent of the, but now of the field. So if sigma were just an n by n matrix, you could have summed up the series easily, and the result would have been a polynomial in X, just this polynomial. But it turns out that in the background of instantons, the products of single traces, these Casimirs, don't behave in the same way as they do in classical for classical matrices. So there are the so-called, so the product becomes a so-called quantum product. There are corrections, and as a result of these corrections, in the background of instanton, this observable has poles in this variable X. And for quiver gauge theory, we'll have many, so we have this observable for each gauge factor. And so they have some poles. And the main claim is that there is a way to adjust these observables, add some terms, which will be products of these Y's, maybe for other gauge factors, such that the expectation value of this dressed observable will be a polynomial in X. And the coefficients will depend on masses of fundamentals and bifundamentals, and so there are many details which I will skip. And one can define the products. So the main claim that in the limit epsilon 1, epsilon 2 to 0, this equation, that the expectation value of this observable is a polynomial in X, becomes an algebraic equation, just like the loop equation for matrix model. And this algebraic equation becomes the Seiberg-Witten geometry of the of that type for this complicated quiver gauge theory. And if you don't take the limit epsilon 1, epsilon 2 to 0, then this becomes a kind of doubly quantized Seiberg-Witten geometry, which reflects the hidden symmetry of the space of vacua, organized into some kind of quantum group based on the quiver. Now, so maybe I'll first give an example of such an observable. So if you take the simplest, maybe the simplest example of gauge group, of gauge theory of the type we discussed, it is sometimes called super QCD. So the gauge group is just SUN, so there is only one gauge factor. It corresponds to the graph, very simple graph, which is called A1. It's a graph which has one vertex and just one vertex, so nothing else, no loops. So there is a 2n flavors of fundamental hypermultiplets, and so this is this factor of 2 makes the beta function range. And so in this case, this fundamental QQ character, this combination of the Y observable and plus correction, which cancels poles and expectation values, is a relatively simple expression. It's just Y plus the instanton factor times a polynomial whose roots are the masses of these fundamental hypermultiplets divided by Y. So the claim is that the poles in one expression cancel the pole in another expression. And in the limit epsilon 1, epsilon 2 to 0, the Dyson-Schwinger equation becomes an algebraic equation, which says that Y of X plus Q is a polynomial X of degree 2n So we can call this polynomial T. And so this equation tells you that y is a solution of quadratic equation in terms of x, and so this defines a hyperelliptic curve, which is the Zybek-Newton curve. So from that you can recover the effective couplings and everything about the low energy effective theory. So the question is, okay, so this is some algebraic construction. So this is some so there are some algebraic identities which are behind this. But what is the physics of this observable? So where does it come from? So this is where the string theory helps. So it turns out that so let's see. Okay, you don't want to hear about brain worlds. It turns out that the way to understand these observables, one way to understand these observables is by embedding the gauge theory to string theory. So if my original gauge theory was a theory on a stack of G3 brains in type 2B string theory with some background fluxes which make a theory not of n equals 4 type, but of this super QCD type, then one can engineer an local observable in this theory by adding a stack, or maybe just one brain, which occupies transversal space, transverse R4. So this transverse R4 inside it will intersect this original R4 at one point inside R8, but in 10 space-time dimensions of type 2B string theory, there will be just some point where these two planes are the closest. And so this point, the observer who lives on these horizontal brains will interpret as a local operator. In fact, very heavy operator, because the whole brain is projecting to this point. And so one can show that these various terms in this expression come from the contributions of instantons which can be attached to one stack of brains or different stack of brains. So the instantons can kind of travel from one to another. And this formula comes from integrating out open strings which connect these two stacks of brains. So string theory is helpful in designing these things, but at the end of the day, these are just, it's pure mathematics. You can, and it was explained to mathematicians, and now they're exploring this structures without recurse to infinite dimensionality of string theory. Okay, so there are many generalizations and implications of these constructions. Some of them are indicating that there are interesting non-local operations which can map one quantum field theory to another quantum field theory, which when I first started thinking about it, actually made me very scared, because what it means that so you go to bed at night living in a world described by the standard model with some gauge group, some matter field, and so on, and then during the night an interface happens, like space-like domain wall, which completely changes the physics. And tomorrow we live in the E8 gauge group, in the gauge theory described by the group E8, and we don't exist because there is no carbon in the universe based on the E8. So we're fortunate that nobody's inserting those observables yet, but who knows? So so mathematically we can study them. Of course, we can study them on the computer. And so they hide very interesting structure. The good news about these observables is that maybe the landscape problem of string theory is not as severe as it may appear, because there are non-trivial symmetries which we didn't appreciate before, which can change the vacuum of flux vacuum, for example. Okay, so the challenge, of course, is to extend these observations and observables to the practical scheme, which would extend beyond the BPS sector, like in the ADS CFT correspondence, and to apply to, let's say, real QCD. But this hasn't been done yet, and I thank you for your attention so far.